So we want to be able to show that a gamma is a conjugate prior for a Poisson. As an aside, it's actually the conjugate prior for several other things as well. So, first thing I suppose we should remember is what is a gamma distribution? What does a gamma distribution look like? Well, and we'll use the same notation that's used in your notes. So we have gamma or v is v to the power of or over gamma of or, y to the power of or minus 1, e to the minus vy. And this is where I said I'd give you a tip as to how you remember which is your first parameter and which is your second parameter. Your first parameter is of a gamma distribution is the one that's inside the gamma function. That's how I remember which is which, if I was just given it like this. Now, if you treat mu as being where the y's are, and r equals the sum of yi's plus 1, and v equals n, and if we treat y here as being mu, you would get n to the power of the sum of yi plus 1 divided by gamma, the sum of yi plus 1. Nah, that's all constant. We're going to not care about that. Mu to the sum of yi plus 1 minus 1. Nah. E to the minus n mu. Well, that's proportional to, because I don't like having to write out stuff unnecessarily. yi e to the minus n mu. Now this should look familiar, as if this was a single draw, that the yi, sum of the yi's is a single draw from a Poisson n mu. So here you can see how, if you think of your variables and your parameters in a slightly different way, you can map one to the other. That's always a good start for confirming that one is likely to be conjugate of the other. The other reasons that you should be thinking about it is, what is the valid range? By the way, that's not sufficient for showing conjugacy. We'll show what is later.